One of the most misrepresented things in movies nowadays is electrical current. For example, as soon as live wires touch any kind of water, it becomes an instant death trap, which, as you can see, is obviously not true. Another example is that once electronic circuits touch water, it gets immediately destroyed, which is only partly true. So to get rid of all those preconceptions, we will conduct a couple of experiments in this video to find out how water and electricity correlate and in which way water actually influences electronic circuits. Let's get started. For starters, let's fill up a glass container with plain old tap water, set my lab bench power supply to 15 volts, connect the multimeter set to current measuring in series, and place the probes in the water to determine how much current will flow through the water dependent on the distance of the two probes. At a distance of around 10 centimeters, we get around 7.2 milliamps, at 5 centimeters 8.5 milliamps, and at 1 centimeter 13.4 milliamps, which according to Ohm's law equals a resistance of approximately 300 ohms per centimeter. That means we could, for example, use the water as a current limiting resistor for a 5mm LED. But besides the resistive aspect of the water, there also seems to be a chemical reaction happening at one probe, since bubble rise to the surface. To investigate this chemical reaction a bit better, let's rather utilize mains voltage, which offers a higher RMS voltage of 230 volts, and thus by placing it in the tap water, much more current flows. Just like before, by shortening the distance between the two probes, the resistance decreases, and thus the current flow increases, which after gathering a bit of data equaled a resistance of around 300 ohms per centimeter as well. But unlike before, we can now observe a more powerful chemical reaction at both probes. And after letting the probes sit in the water for around 20 minutes, the surface of them suffered quite a bit, and even revealed a bit of rust. The problem is that tap water does not only consist of the water molecules H2O, but also of cations like calcium, magnesium and natrium, which possess a positive charge, and anions like carbonate, hydrogen carbonate, chloride and sulfate, which possess a negative charge. Those additives not only make the electron flow, aka the electrical current through the water possible, but also create an electrolysis. I'm certainly not a chemist, but in a nutshell, it means that the water ions react with the probe metals in order to create oxygen and hydrogen, which are the bubbles, while the probes slowly corrode and thus become less conductive, which could be a potential problem for electronic circuits, but more about that later. For now, let's prove this theory of the additive's function by filling a second container with distilled water, which more or less lacks all the ions and only consists of H2O. By varying the distance of the DC voltage probes to one another, we get current flows of around 50 microamps to around 70 microamps at best, which would equal a resistance of approximately 30 kilo ohms per centimeter. That is 10 times bigger than normal tap water, which showcases that the additives make water conductive and also reactive, since this time there's no visible chemical reaction happening. To end this first experiment, let's try the mains AC voltage once again. The current flow varies from 1300 microamps up to 1720 microamps, which once again equals a resistance of around 30 kilo ohms per centimeter, which is again 10 times bigger than with tap water. And by observing the probes, there also seems to be no visible chemical reaction, and thus no problem for our probes. So putting electronic circuits into distilled water should work without a problem, right? Well, let's start small with the most basic passive components: a resistor, a capacitor and a coil. By utilizing a transistor tester, We can, like usual, measure the resistance of the resistor, the capacitance of the capacitor, and the inductance of the coil. And to my surprise, after placing the components either inside the tap water or the distilled water, the measured values of the transistor tester did only vary slightly. The reason could be that the leads of those THT components are pretty far apart, and thus the equivalent resistance of the water did not interfere enough. But what about a small Arduino Pro mini board that features components and PCB traces which are very close to one another? So I programmed two Arduino Pro minis to let its onboard LEDs blink every second. After then adding wires to the 5V and ground pin of the microcontrollers and powering them with my lab bench power supply, I started by submerging the first one in tap water. Right after the submersion though, the LED stopped blinking, and even after lifting the Arduino out of the water, the microcontroller did not want it to work correctly anymore. But for now, let's keep it in the water to later analyze how similar battery-powered electronics would have reacted underwater. So let's try the same experiment with the second Arduino and distilled water, which to my surprise also immediately stopped working once it was submerged. Resetting the microcontroller did not help either, but after letting the Arduino sit in the water for a couple of seconds, it started working again. Seems like complex electronics can work in distilled water, just a bit unreliable. And while observing the now functioning Arduino, I noticed that there are almost no chemical reactions, while the Arduino in tap water looks like it's slowly dissolving. So let's get both Arduinos out of the water. And after drying them off and powering them once again, I noticed that both microcontrollers still functioned without a problem. The only difference is that while the distilled water Arduino still looks brand new, the tap water Arduino corroded quite a bit, which in the long run could have probably destroyed it. As a last experiment, I soldered two wires to a small SMD capacitor and charged it up with a voltage equivalent to a LiPo battery voltage. As you can see, after the charging, no more current flows. But if we add tap water to the setup, we can observe the by now well-known chemical reaction, which lets current flow once again. After 30 minutes in the water, I wiped off the water and noticed that there's now a constant leakage current due to the long electrochemical corrosion, which can, for example, drain the battery of your electronic circuit slowly. So all in all, water and electricity/electronic circuits are certainly not best friends, but they are not as dangerous together as people usually say. And by coating electronics in various materials, you can even make them completely waterproof. But that is a subject for another video. Until then, don't forget to like, share and subscribe. Stay creative, and I will see you next time.